Again. What we're going to do now is we're going to start video 33, and this is intro to multiple regression. And what I want you to think here is we're going to have p minus 1 predictors. So instead of having one predictor, we're going to have multiple predictors, hence multiple regression. And the reason I do p minus 1 predictors is it's pretty standard procedure in multiple regression textbooks. Some use k predictors, but nevertheless, the p minus 1 predictors allows for the addition of your intercept beta 0, which would give, in a sense, p betas. Guys, the model we're going to look at is going to be y sub I, beta 0. Plus beta 1 x1. Well, let me go ahead and do this. Beta 2 x2 plus, let's call it beta p minus 1 x p minus 1. And of course, we've got to have the error for the term. So that's what our model is going to look like. And I mean, you should know by now that the expected value of our y sub I is just going to be equal to, I'll tell you what, it really annoys me when I run out of space. So this is going to be beta 0 plus beta 1 x1 plus beta 2 x2 plus beta p minus 1 xp minus 1. Yeah, you might, think in the educational setting, if we wanted to predict a person's college GPA, well, what we may want to do this from is we may want to let B1 be the high school GPA. We may want B2 to be their ACT or SAT. Beta 3, which actually, believe it or not, is a very good predictor of college GPA, is mother's and father's education level. So, we could come in with as many predictors as we like. Well, I think we looked earlier at a simple linear regression model where we would predict the miles per gallon of a car. And you might think of multiple predictors we could use there, including weight, horsepower, and just different things. All right, gang, the parameters for these models, as you would expect, would be beta 0, beta 1, beta 2, and beta p minus 1. And the interesting part of this is our predictors can be quantitative and or categorical. So the multiple regression model permits us to put gender, socioeconomic status, if it was categorized, political party, religious affiliation, variables like that in. Now, if we get in a situation where our categorical variable is dichotomous, zeros and ones is usually the way we code it, like gender. The technique is not that difficult. And in fact, it's very straightforward. However, if we get into a situation where we have categorical data where we have more than two subcategories, if you will, subgroups, now we get into something called dummy variables. So I'll probably illustrate that in class. So guys, the beauty of what I've tried to do so far is I've tried to set a very solid foundation using matrix methods for simple linear regression. The fact is, if we have a firm, solid foundation for simple linear regression, then multiple linear regression follows suit. For example, our response vector is still going to be like this. And our design matrix is going to look a lot like what we had before. Close this up here. And so our design matrix has, got a little bit more going on. Obviously in a simple linear regression case, the design matrix would stop right here. But in the multiple regression, we clearly have more going on. All right, gang. Another, remember the coefficient matrix? Well, it's going to look, again, a lot like before, except we're just going to have more betas. Our error matrix is going to look just Doug. Is going to look just like before. And same things apply. We want our errors to be random, and some of the errors to be 0, some of the errors squared to be a minimum. And guys, at the end of the day, we still have this driving our calculations. Now, let's see, what do we want to do? All right, what I think I want to do next is let's consider estimation of the regression coefficients. And, if we have, for example, our data x1, y1, x2, y2, and let's say that we just say that we have n ordered pairs, then from a least squares perspective, we could see that we could, using a similar notation, that we could minimize and I'll tell you what I want to do. I want to change gears on you just a little bit, and I want to do that to get you familiar with both notations. So we have K predictors, and the reason is I know what's coming up, and it'll make things less messy. So guys, here, if we were going to minimize Q through the least squares approach, what we would do is we would take the derivatives, and we would come up with the normal equations. And so guys, if we have K predictors, then we'll have K plus 1 normal equations. Now I'm going to go to the next screen here because there's going to be a lot to write here. So, just like before, when we have a simple linear regression, I hope you know that we would have beta 0 n plus beta 1 some xi's, some y sub i's, and we would have beta 0 some xi's, beta 1 some xi squared, and this would be, of course, some xi yi. And what we saw, I think I did this in class for you actually, is that we could look at this as a matrix. All right, and ultimately what we could do here is we could solve for the estimates by taking, and I'm going through this really, really, really fast because I expect you to already know this. All right, so we saw that in class that we could we could do this. Now, guys, what I want to do obviously is I want to extend this to a multiple regression. So now, guys, I'll slow down now. Okay, I'm writing really fast because I expect you to already know this. So, guys, what the normals are going to look like here will be beta 0 n plus beta 1 some xi's plus dot 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 beta sub k, or p minus 1 if you prefer that, but ik equal the sum yi's. The next one will look like, just as you would expect, or I hope you would expect that. This is hard to write this small. I hope you see that's a K. See how messy it would have been if I'd stuck with p minus 1. And final. Gonna run out of space here to daggone it. Yeah, I'm trying to not let it happen, but anyway, it's going to happen. So. Okay, so yeah, this is what our normals are going to look like. Now, I mean, that notation can be a little weird, especially like, well, what does this, like, I'm going to circle this right here. What does I sub 1 mean? Well, that just means that you're running through the x sub i's for the first variable. So x sub 1, 1 would represent the first piece of data from the first variable. X sub, for example, 2i would, or I'm sorry, 2, 1 would be the second piece from 1. the first variable x sub 2, 2 would be the second piece of data from the second variable. Now, I think it's going to be worthwhile if we run through an example for two predictors. And I would really, really, really like it if, hold on, I gotta get a cup of coffee here. Oh, hopefully I'm not slurping. I think I just did. So if we have two predictors, so ultimately we're trying to go y equals beta 0 plus beta 1 x1 plus beta 2 x2. So, if we have this, first of all, what's Q going to look like? Well, we're going to try to minimize the sum of the vertical distances squared. And I'm not even going to attempt to try to draw that. And the normal equations would, of course, look like that should be xi1. I'm getting sloppy here. Alright, the next one would look like, now again, let's think. I'm going to erase this. We have k equal 2 predictors. So we're expecting k plus 1 normals, okay? And that's, of course, exactly what we're going to get. Alright, gang, the next one, of course, there should be no debate whatsoever what goes first. And there should be no debate what goes next, because we can use what we've hopefully learned. Daggone, I keep forgetting that x sub 1. But, there could be a little bit of confusion what goes right here. Some xi,y,i. And the third one, which, if you, well, let's see, I forget, this could be xi2 plus beta 1, some xi2 xi1 plus beta 2 some i2 quantity squared, and of course this is going to be equal to xi2. Wait a minute, gang, don't forget this up here. This should be I1, okay? And y sub I. Okay, let's just run through an example here.